Good evening, everybody. Thanks for coming down. So we're delighted to be along. Thank you for inviting me along, Jeff. I'm here today to talk to you about the heat exchange pile foundation solution at Euston Station for HIPER 2. My name is Stuart Norman. I'm Managing Director for Keltbray Piling. They say everybody rises to their level of incapability. So I've been Managing Director now for 12 years, so I seem to have found mine. But yeah, delighted to be here. So thank you very much for inviting me along. Good, that's working. So the journey for the HIPER foundation solution, I'll talk to you a little bit about that to start off with, and then we'll get into the first use over at Euston. We started in 2018 with a grant application to Innovate UK as part of the Transforming Construction Challenge. That was a grant fund of about 36 million, and we were very fortunate to be awarded around about £500,000 in funding, which we had to match ourselves. So overall, it's just over £1 million worth of funding required. We were the development lead for the project, and we were required to have one SME partner. So that was Converge, and the other an academic partner, so that's City University of London. And we also roped in the likes of GCore Limited, SEM-Free, because we were pushing the use of ultra-low carbon concrete at that time as well, and ARUP as peer reviewers for the project. So that completed in 2021. So there's a bit of a delay with COVID and things. So we had a 3-month extension, and we were able to push that forward to kind of, if you hear so many new acronyms at the technology readiness level, TRL level, around about kind of 6, ready for a TRL level 7, which is the first use in anger, the first demonstration project, which we were lucky to have with HIPER 2 at Euston Station. That was what I was just talking about there in terms of the initial partners. Ourselves, City of University of London as development partners, GCore, Converge, SEM-Free and ARUP. So we were given the opportunity to demonstrate our innovation at the Euston Welfare Facility for HIPER 2. This was back in 2021, early part thereof. For main contractor Maestro Gardos, engineers for the scheme were Wentworth House with check-in engineers ARUP. We were the piling contractor and also the enabling works contractor, as it turned out as well, and the support of the various subcontractors there and development partners. Just to highlight some of the HIPER 2 project targets. That's a bit better, isn't it, for you? There you go, a bit bigger for you. HIPER 2 development targets. So net zero by 2025 is their key aim. A 50% reduction in embodied carbon and 100% zero carbon electricity to power the trains. So as you can see, there's a high demand for a reduction in both embodied and operational carbon coming from the client, as well as the desire to adopt renewable energy sources. So net zero by 2035, sorry, not 2025, is the stated client's aim. So the welfare facility has been set up as part of the main Euston Station development, which is ever ongoing in terms of contracts starting to be let. And we were required to put in the welfare facility. So this is the location of the site, obviously Euston Station. The opportunity that we had was at the Maria Fidelis playground, so an old school, which is not in use anymore. This area was identified as the ideal location for the welfare for all the workers to during the construction of the HIPER 2 new HIPER 2 station. Little pictorial view there on the left hand side of what it's due to look like in terms of the welfare facility, kind of a 5-6 story modular construction. next to the existing Maria Fidelis School. And the intention, I believe, is to utilise both of those buildings for the welfare for the construction. So site geology, relatively typical London clay geology. London geology, made ground over London clay formation. The Reading formation was around about plus 2.5, so a bit water bearing a little bit further into that Reading formation. The Up Nor, which we didn't go anywhere near, and Thanet Sand and Upper Chalk. So the pile lengths themselves are around about kind of 25 metres, but we'll come to that in a second. Lots of constraints on the site from existing LUL tunnels, and then new proposed kind of Crossrail 2 route was just off to the southeast. There was an existing Thames Water sewer, which you can see is that kind of little orangey sewer running through the middle of the plot there. So that kind of divided what was already a small site into two halves again. And the foundation options that we looked to develop together with Wentworth House, the client came up with a number of different requirements for us. So we looked at a traditional pad option, and we looked at option 2, which was mini piles. Option 3 was just a raft only, and option 4 was for a pile assisted raft. Movement criteria were relatively tight. The first option was kind of 600 mil square pads, not 6 square meter pads, 300 mil thick. Mini pile option was 450 mil diameter mini piles, generally to 16 to 24 meter depth, quite a lot of them. Option 3 was a 600 mil thick raft, and option 4 was a reduced number of 900 mil diameter piles, either side of a half a meter thick raft itself. So the idea was to utilise the option 4 so that we could utilise the HIPER piles as well, and that together that limited the overall settlement of the structure. So what we'd been developing for a number of years now, by the time 2021 came around, was the HIPER pile. So split down into a number of different components: the hollow element, impression, precast, energy and energy generating and reusable pile. But this was the first time that we thought about utilising all of those options on one particular site. Matches pretty well with the client's ambitions to reduce the embodied and the operational carbon, which we'll come to in a second. But the whole idea really is for the first time to be able to come up with a foundation that was fully reusable. Longer term lifespan, the client has to give the site back to Camden Council, I think it is. So we've been in discussions about the use and the reuse of the piles. The questions come back, how much is it going to cost to remove these piles? So you don't have to remove them, you can just reuse them. So that obviously that discussion will go for the future. But we're going from a pretty simple, dumb foundation that's not really developed in the last kind of 40, 50 years. The last kind of major innovation in piling, you could argue, was maybe sort of diaphragm walling, CFA piling. Rotary bore piling has been around for a long time, but we just tend to do the same thing. We drill a hole, we put a load of rebar in, and then we fill it with concrete. And what I like to think about is the foundation concrete of a typical structure is a bit like an iceberg in terms of embodied carbon. You put an awful lot of carbon, an awful lot of concrete in the ground, and you forget about it. And people are there thinking about, well, how can I reduce my slab thickness from 300 to 250 mil? How can I play around with my limited amount of concrete on the upper floors, where actually you've put a whole load of carbon as the iceberg in the ground before you even get started. And people don't tend to challenge that because, well, it's the foundations, it's risky, we don't mess around with the foundations, build off solid foundations. How many times have you heard all those kind of sayings? So we look to challenge that as part of the HIPER pile concept. The hollow element itself, depending on the diameter that you're replacing, can save up to 70% embodied carbon. The minimum diameter for the hollow piles, we tend to start at is around about 900 millimeters. Otherwise, you're just not really saving much carbon from the 300 mil void in a 750 mil diameter pile. The impression element has been designed to perform a key into London clay soils and over-consolidated clay soils, and that in itself increases shaft friction by up to 40%. That gives you the opportunity to reduce the diameter of the pile and create shallower piles themselves. Actually, as it turned out, quite ideal for these ground conditions, because a 25-metre depth pile was about as deep as we could go before we hit the Lambeth group and before the water would enter the pile. And then you'd be thinking about options for stabilising the bore, whether it's polymer support fluid or bentonite support fluid. So actually we're able to enhance the pile friction to keep us nice and dry and stable. The precast element is pretty much designed to embrace modern methods of construction. So generally the 90% of the pile is fabricated off-site. The only bit that we do is grout the skin of the pile between the precast element and the ground. And again, I've got a couple of slides on that to show you shortly. The energy component, quite a simple concept, but the idea is that we fill the void with water, which is actually very good at conducting heat to and from the ground. And we put geothermal loops inside the water, and we pass hot and cold water through those loops, and it disseminates the heat through the water, through the concrete into the ground. And again, I've got a couple of slides to show you on that as well. And the reusable element, like I say, really trying to embrace a circular economy for deep foundations for the first time. A lot of my time is spent looking at new pile foundations, where there are now, certainly in London, a lot of existing pile foundations, and can we reuse them? It's very difficult to reuse them because the quality of the records isn't there, and you can't get access to them until you demolish the building, and then you're on the critical path. We'd love to mess around taking samples and doing cores and all the rest of it, but the program just won't allow for that, particularly when there's so much uncertainty as to what you might find. So we developed the design together with Wentworth House. Like I say, I think that the grey element on the right is the depth of the piles, and we kind of just went to the nearby depth of the London Underground tunnels. Not that close, I must add, but it was one constraint on the site itself, and lots of kind of funky little 3D images of what we were able to design up front. So I cycled back to the kind of 2018 and the need and the desire for an academic partner. What we wanted to do, we had the concept in about 2017 for the impression pile to increase the shaft friction on bore piles themselves. So we went to work with City University. There are a few different types of shaft enhanced piles on the market. So CHD piles you might have heard of. And there's kind of sole thread and things like that which are on the market, but the majority of them are pretty unreliable. CHD pile itself struggles a lot from boring through gravels and then going into London clay. And what we wanted to create something that was reliable, easily inspectable, and something that was repeatable. So we couldn't do that by just boring into an open hole because of the mess and the uncertainty that would create. So we wanted something that was of high quality. So we came up with the idea of an impressed bored shaft. So generally the process is you bore the shaft as normal. We then switch over to the impression tool, which is a number of jacks built into the tool, and we go down and make an indentation into the soil. So just take yourselves back to when you were a child and you had a little clay pot, put your thumb in the clay pot and you're able to remold the clay. So that's exactly what we do. And that clay kind of remolds itself around the shaft, and we compress that as we go. So there are limitations on the strength of the clay that we're able to remold, but typically the clay is softer at the top and harder at the bottom. And where do we want to remold the clay? We want to remold it at the top, because that's where we get that's where the load comes on, and the resistance comes from the ground first and foremost. In order to do this, we had some excellent input and a funded PhD student, a guy called Leonardo, who's written a number of papers now on the performance of the impression piles. But we did all this at small scale. I think it was about 1/8 scale, although my memory may tend to fail me in that regard. And we did about 72 centrifuge tests So we had a lump of kale and clay. We're able to spin that up to normalize the pore pressures, and then we bored into the clay using it as a particular small little tool, and we fabricated these little piles out of resin with the little nodules all to the right scale, and then we load tested them against a standard straight shafted pile. And what we're able to see is that precise modelling of what I said earlier, around about 35 to 40% enhancement in shaft friction. It's now subsequently been checked and proven and interrogated by ARAP, and they understand how these piles work, and we understand how these piles work now as well. So it's all about effectively optimizing the distance between the nodules. So it's managing the depth of the impression tool and the rate at which it would then impress into the soil. And what it does is it moves the shaft friction from a clay to concrete interface, which is relatively unbonded. That's why, for those of you with any geotechnical design experience in London clay, would have an alpha value of 0.5. So the shear strength of the soil, you divide that by 2 effectively, and that's your friction between the concrete and the clay. And we're moving more towards a soil-to-soil interface. So that's where you can see that the ribs of the pile or the nodules of the pile moves that shear interface outwards, but without actually putting in the concrete that's associated with that pile diameter. So that's how we're able to get an enhancement in shaft friction, and thereafter reduce the amount of concrete that goes into the ground, and therefore reducing the embodied carbon. So that's the tool itself on the left. We inspect the piles by GoPro camera. So we put the camera down, and that's typically what we'd see. We'd see a nice little shelf made into the clay. The driver himself's got a little red light, green light, so he's able to see, pull the tool up 1/2 meter, press the button, pull the tool up 1/2 meter, press the button. So we bore the shaft, we put the tool to the bottom, and then we press as we go. We did a load test on the site itself. We were expecting an alpha value of 0.7. So we actually installed a hollow impressed pile, cast in situ. We're expecting an alpha value of 0.7, so that's a 40% increase from an alpha value of 0.5. We actually got an alpha value of 0.77. So it's over a 50% increase to what you would normally expect for a standard board pile in London clay. Yes, it's a little bit more fiddly. I often get asked the question, how long does it take to actually impress the pile? It takes around about 15 to 20 minutes per pile. And we can run that machine either off the piling rig itself or off the attendant crane. Normally when we're piling, the attendant crane does pretty much nothing. It lifts the cage every now and again. So we're trying to optimize the utilization of the equipment that we've got on the site to keep the rig boring and keep the crane at least partly active. There was 5 levels of strain gauge in that pile, so we had some really good data as to how the load shed itself down the pile itself. So bringing those 2 elements together in terms of the hollowness and the impression element, why are we doing it? Well, if you look at the dark line there, that's typically the solid structural capacity for a concrete strength of a C3240 or a C3545. You can play around with the structural capacity of the pile itself. And the dotted line is typically the geotechnical capacity. So we design for both of those things when we design piles. The bit in between the dotted line and that top solid line is waste. Typically we put very large piles in the ground because we want that perimeter in contact with the soil to generate the geotechnical capacity. But then we fill it with a whole load of concrete. So we over design for the structural capacity. So what we wanted to do was narrow that band into that little orange band that we've got there, which is the optimized capacity. And that's the whole thing around the hyperpile, around the hollow and the impression elements of the hyperpile itself. But what to do then with the void? So I spoke earlier about filling that void with water. And what we've seen from the tests that we've done and how we designed the piles at Maria Fidelis is that we designed the piles for the thermal capacity, the structural capacity, and the geotechnical capacity. And we optimize the design based on those 3. The client's requirements were for particular heating and cooling load, which I've got later on in the presentation here, to heat the building, to cool the building, and to heat the hot water in the building. And we're able to do that from all the piles themselves. Typically, you look at a scheme, whether it's in London or in a built-up environment, you would have either air source heat pumps and piles, or you'd have piles if the building's tall enough and the ground's poor enough, obviously, with shallow geothermal boreholes, so typically 150 to 200 metres deep boreholes. The advantage of a geothermal system, whether it's the deep boreholes or now the HIPER system, is that you're able to play around with your plant rooms. So typically the plant rooms for a geothermal system would be on the ground floor, whereas the plant rooms for an air source system would be on the top floor. Whereas the most prime residential prime element for utilising and getting your value back for your building is typically on the top floor when you're looking at offices or flats or whatever. So the testing that we've done is basically two of our piles, typically a 900 mil diameter pile here on this occasion to just over 25 meters, will give you the same thermal capacity as one 200 meter deep thermal borehole. The outputs would typically we put in about 4 piles per day. The outputs on a geothermal borehole will be 1 or 2 boreholes per week. So you start to think about the numbers and you start to do the maths and think as an overall program where you have a thermal load requirement and a structural load requirement, it starts to come into its own. So this is the thermal scheme, a relatively small one by today's standard at Maria Fidelis. The peak heating was 40 kilowatts, the peak cooling was 147 kilowatts, and the annual cooling demand was 140,000 kilowatt hours. So again, if you do the maths and you compare that to a direct electric system, electric these days is costing us all 34 pence per kilowatt hour. And the cooling energy saving over a 12-year period will be around about £500,000. So it's really unfortunate that we didn't do the calculations for this before we tendered the scheme, because we would have added £500,000 to the cost of the piles. But hey ho, you live and learn. So some pictures there of what the scheme actually looks like in situ. This one here is a bespoke prefabricated cap that we fit to the top of the piles. You can see here you've got 1, 2, 3, 4 loops per pile. So we form the pile, we fill it with water, we install the loops, and then we cap it off. We put that plastic cap on the top. We seal that cap in, and then we're able to pump either hot water or cold water into those loops. They cycle around the pile one by one by one by one, and then they come out and they all go to a huge kind of manifold type thing, which is this picture on the right hand side here, with all the loops get gathered together. The way that we designed it was to have that pipe work underneath the slab. So in the drainage layers you typically have. So we'd engineered the levels pretty well, so that when we cast the slab, it just buried all the loops, so they weren't damaged. The advantage of this is there's only one test required. So we come along, we do one pressure test, we test the system, we move on to the next one. The pipes are installed away from the main piling activities, so there's not that crossover of the piling gang and the thermal gang, and also because of particularly the precast system, it's impossible to damage the pipes when you're breaking down the piles, because that is a separate exercise that's done before you put the loops inside. You look back at what's been done in the UK at the minute, the ground source system is there, but people don't use ground source loops because they always get damaged. Certainly when you put them in piles, they always get damaged when you break the piles down. So we've completely eradicated that as a problem. So a quick slide on the project outcomes. We installed 40 piles. 35 of those piles were a cast in situ HIPER pile. 5 of those piles were a precast HIPER pile. So you can see some of the precast elements just lying on the deck there. That is a precast and a pre-stressed strand system. So effectively, a bit like Lego blocks, we drill the pile hole and we stack units from the bottom upwards, and then we pre-stress them together, and then we fire grout down the recesses in the structural wall of the pile itself, comes out the bottom of the pile, and it grouts from the bottom upwards, just like a little curtain wall coming up to the surface. We then obviously fit the pipe work and everything else and fill it with water. So again, you can see in that middle picture, just one of the cast in situ HIPER piles there with the loop starting to be attached, and then all the loops kind of gather themselves before they go into the manifold there. So what did we achieve? We achieved around about a 40% saving in embodied carbon as opposed to what you would have done based on a solid 900 mil diameter scheme. And then the operational carbon savings we'll be monitoring for the next 12 years. The project will be live monitored over the next 12 years, so that data will be publicly available. The units are still being built and still being stacked, but we believe the system will be turned on sometime in the summer before things get too hot, so they can use the cooling energy of the piles themselves. So some feedback, great feedback from Heather Donald, Ben Wielden, MDJV Program Director, Alex Rose as well. So the success of this system has led to us being awarded 5 further contracts for High Speed 2. Not all of them have all of the elements of the HIPER pile. Some of them just have some of the impression elements themselves. And then just one final picture showing some of the elements there. You know, we believe we're onto something that's going to change the industry for the better. The difficulty that we have is education. Education of the clients over the value, over the whole life cycle, over the circular economy, rather than just buying the cheapest thing that you can possibly see at the time and then wasting it later on. So particularly like that quote, you know, to change something, build a new model that makes the existing model obsolete. So with that, I think that's my last slide. There's what Euston looked like about 4 or 5 months ago. But if anybody's got any questions, I'd be pleased to answer. Thank you very much for listening.
Thank you very much. As I said, I have 1 or 2 questions. If you just maybe repeat for the audience.
Of course, Jeff. Yeah.
How did you ensure / demonstrate continuity between the precast and the soil itself?
So how do we demonstrate continuity between the precast and the soil itself?
Air voids and pockets and things like that.
Yeah. So we were fortunate because this was our first one, kind of proof of concept, if you like. It was a pile generally that in dry bored London clay. So the diameter of the pile that we bore is 900 millimeters for the precast element. The precast element itself is 800 millimeter in diameter. So we've got 50 mil either side. When we pump the grout through, we're able to visually see the grout rise up on the outside. Within the next 4 weeks, we'll be doing our first pile, which will be under support fluid. We'll be doing exactly the same thing again, but pretty much in the dark, and displacing the support fluid upwards as we grout it from the bottom of the pile.
Was there any significant grout loss when you were carrying out the operations?
There was for the first 2. I think there's a bit of inside knowledge there, Jeff, maybe. So the first 2 we had, my background is in piling. It's not in precasting or precast concrete construction. And it's amazing how you look at the quality of those first units that we manufactured, and the quality of the joints was not good. So as we were grouting up our nice little hollow that we'd managed to create, we had a whole load of grout firing in like little jets coming in. So, well, where's that coming from, you know? And that all went back to, again, certain elements of the pre-stressing weren't working because they were overstressing the concrete. So it was all very much a learning as we went. The last 3 actually worked perfectly. So we managed to get the correct pre-stress into the system, and we grouted up on the outside, and there was a nice hollow void in the middle that obviously we then filled with water.
They're very slow on the questions, Stuart, so
you keep going, Jeff, or if anyone else has got any other in here.
Just in relation to analysis on carbon savings, has there been any work on that yet?
So the analysis on the carbon savings, we use the EFFC carbon calculator, which is common across the Federation of Piling Specialists. And we demonstrated a conforming scheme. If you'd have put in, I think it was 25 meter long, 900 mil diameter solid piles versus the 22 meter long on average 900 mil diameter hollow piles that we put in, even with some of the steel liners that we put in to form the voids for the cast in situ, we were still around about 40% embodied carbon saving, a reduction from 40% embodied carbon.
You know, my question was on a similar track, and that was, you talked about what, £500,000 saving in terms of heating and cooling.
Yes.
What was the financial saving in using this form of pile as opposed to the traditional pile?
Yeah. So the financial saving of using this type of pile versus a traditional pile. I haven't got the slide with me, but we did a whole suite of calculations looking at if you'd got the energy from a traditional shallow geothermal system, it would have cost you whatever it costs. I think it's £15,000 per borehole. You would have needed 5 or 6 boreholes on this particular site for the loads that you need, plus the cost of the standard solid piles gives you a number, and we pretty much matched that for the HIPER piles in terms of the overall number itself. So the overall the piling element itself was more expensive for the HIPER piles, yeah, but the overall value of what we were giving was slightly cheaper compared to the thermal boreholes plus the solid piles themselves. Hope that answers a question.
Yeah.
A couple of questions really. One is about limiting skin friction in London clay.
Yes.
Because when I used to design piles a long time ago, we were looking at sort of 110, 120 kilopascals.
Yeah.
Is there any evidence that this system sort of ups that value?
Yeah, from the test. So the question is there any evidence that the kind of the average 110, 120 kPa shaft friction in London clay, as you normally design a London clay pile 2 as part of the LDSA guidance? Do we have any evidence that that's greater? Out of all the tests that we've done, we can discount the 72 centrifuge tests because they were done in kaolin clay. We've done around about 20 to 25 actual large scale in situ tests in London clay, and we're getting to around about a peak of 150. So about the peak that you're allowed to take in terms of LDSA is 140. So we're getting just ever so slightly more at 150.
Okay. Second question is, could you tell us something more about the reusability?
Yes. So question on reusability. The intention is, whilst the building is in operation, you may have a slab. You've got some good records, so you should know roughly where the piles are. The intention is to core through the slab whilst the building is in operation. Put a little camera down there and just inspect the pile from the inside out. Is it as deep as you expect? Are there any defects in terms of concrete? If you want to take a little probe from through the side of the pile, you can inspect the quality of the concrete whilst it's in situ and whilst the building is in operation. So you can then design that into your new system for your new building to say, actually, my loads are this and my loads are that. If your loads are higher than the existing system, you can choose to put new piles in, or because the hollow piles are hollow, you can choose to core through the bottom of the hollow pile, which is solid for the bottom meter, and extend the pile down to a deeper depth to at least reuse it once. And then if you want, you could fill the whole thing back up with concrete and steel.
So the big advantage is you don't have to core it because it's already cored.
Exactly. Yeah, exactly.
Anybody else?
Yes. So the question is, the precast segments are 800mm diameter. What length do they come in? Yeah. Yeah. So
they have a spigot and socket, then when you that one down on top of the other, you have male and female. Is that the way?
Correct. Yeah. So they.
You asked a question about the
yes.
The joint is off, where where the manhole. How do you ensure that? So you're looking down, like you're looking into the abyss. I know you have a camera. You're lowering it down. How do you?
Yep.
Do you use kind of like on the actual say you let down the male first, or the male first, then you have your solid, then you have your ridge right on top of it.
Yeah.
You have a big kind of like a water bar or kind of like a hydrophilic, and you jam
yes.
it.
Yes. So some really good questions there. Some really good points. So I mentioned those first 2 piles that we did there, Jeff, in terms of the quality of the construction. When we manufactured the first ones, they were pure flat joints. There was no.
If it didn't come from or out of line, you were on.
We were buggered. Correct. So the revised detail that we have is a male and a female joint. It incorporates a water bar. And the clever bit of the system is when we put that first solid piece down to the bottom, it actually takes the pre-stressing strands down with it. And we then...
And I wanted to get a certain thing. So say you come down, you have your first half meter or whatever you have full, and you come down, we work with your
yeah.
You come down with your, let's say your first one right down. So obviously you have your wire and you have your anchor at the bottom. So you load that down one on top of the other, and then you come to the top and you stress it.
Yes, correct. Yeah.
What would you pull it? I just think the health and safety. I know you have to have a cage. You know how do you do that? Because like bear in mind we're on a vertical pull.
Yeah.
So you have your jack.
The jacks, jacks go over the the jacks go over the strand itself, and they react off the concrete unit.
Pull off the bank.
Yeah. And then they pre-stress. So we typically pre-stress to 150 to 200 kilonewtons, and then the strand jacks cut the strand, and we retrieve it from the hole.
Then when you come to the top of your pipe, that picture you have at the bottom there, that mini picture, that's kind of for all the world part of my phone. It's like the top of an AJ. Is that what it's like the top of a pipe? So you bring up your pipes, and then is that like a riser? You can rise that up and down to suit the level.
Exactly. So the whole idea is that we
do your levels, and
the whole idea is we finish plumb at the right level. So there's the talking about the value of one system versus another.
When you bring your for all the world, like you have a manifold in and out, right? So you have a hot and cold coming up to the pile, and it goes into the slab back to your units and the thing. You have tracers on that to say if there was a leak. For instance, say you doing your piles, and we were doing the concrete kind of line, and we do waterproof, we've done a waterproof membrane. Let's say you come along and then you do your 0.2 cracker.
Yeah.
Say some person for some reason damaged one of the cores. Damage are them pipes like the pre-stressed strand are like the manifold in out, are they in a kind of a coil or something like that? Are they protected?
So those are HDPE plastic pipes, so fairly rigid, but really
1.5 mil wall.
I don't know the full thickness, but reasonably ductile. So you don't want to be smashing into them with a peck or anything like that. But they're full of
vibrator.
Yeah.
Damage.
No. No.
No, I thought maybe you'd have a tracer on them that come back that, you're like a heating system, you'd have to power the water so that if something did burst, you'd lose the pressure.
Yes.
So you know then.
So it all goes back to a very intelligent building management system. So they can trace, you can turn different piles off if you wanted to.
This is your 480K save here. So you know you're getting it.
Exactly. So I mean, our advice is that there is a little top-up system in case there's any water that leaks out of the piles themselves. Same as a heated system in your house, exactly.
Last question.
Yeah.
It is the last question.
One interesting question. It seems a brilliant system. Everything's great. But what can go wrong?
Yeah.
Can you tell me, like, no matter what system we ever come to about, like, there's no such thing as a silver bullet.
No, there isn't. And
what would you look out for? What's the downside, or what?
So
it's an excellent system.
Because of its infancy at the minute, the productivity is not the best. So let's say on this project here, we were limited to 12 vehicle movements per day. So we were getting, if it was a solid pile, we would probably get 3 or 4 piles per day. Yeah, we were actually getting 3 of the cast in situ piles per day, so pretty much matched. And like I say, and for the precast ones, these are the first ones we ever did. What can go wrong? We put that base piece down and it twists because of the spin on the rope on the crane. So that twists, and then you said, well, how do I untangle that mess? 25 meters down. So it was taking us a long time to do that.
When you were letting them down, right? We're doing that to put you and the wires, right? And it can go like that because it's a hole, and it might be clay.
Yep.
You have a different borehole, which we're doing not putting you put down. You're taking it both sides. We're doing not just put in as a boss member valve. They head down. It has to go.
It has to go. Yeah, indeed. But
you won't get that back.
No, but it might spin because it bounces off the wall of the pile and stuff like that. So we've actually developed some fairly intelligent temporary work systems now that monitors the installation of the unit itself and basically stops it from spinning. Yep. Yep. So all these little things that we learned and we picked up along the way. And
Last question. There is one from the online audience. It's from Chris Chapman, and he was asking, was there any capacity of the piles from a lateral load or tension perspective? So did the pre-stressed strands work like a traditional pipe hinge?
The answer to the question is yes. There is, again, the beauty of the pre-stressing system, as most of you know, is you lock in the compression in the pile itself, and by that you give it a certain amount of lateral and bending capacity. If you follow your NM curves, and you'll see exactly what you get. On this occasion, because it was just a simple pile draft, the lateral loads were nominal. So again, it's all about reducing the risk. This is the first time we've done it, so we didn't want to put in the piles as a retaining wall and things silly like that. We just wanted them literally just to act as compression-only elements. There's all sorts of different opportunities, you know, things like tension piles for basements that are either under heave. You know, where does that short-term heave come from? It comes from the fact that you excavate the clay, and then the rest of the clay tends to heave. Well, for the precast element, we don't have to grout up the bit of the ground that's heaving. So you haven't got that tension in the pile itself. You just leave that ungrouted. So there's any number of opportunities and ways that we could take this.
Okay.
Any other questions? Yeah.
One more.
You might just go over again how the whole thing comes together. You're saying you have a precast version and you have an in situ version. The precast version, you put in, like we said, your pipes. You put in your machine first to put your dents in the clay.
Yeah.
Then you put in your precast pipes, if you like.
Yeah.
And you grout between the precast pipe and the clay, and that fills the and what transfers the stress from the clay to the precast bit through the grout. How does that work?
Yeah. So if you look at your structural load, it's going to come on predominantly on your precast element from the top. Yeah. So you look at the perimeter of the precast unit and the bond area between that and the grout, and actually again, you look at all your structural codes, and your bond value is actually very low. The stress between the grout and the precast is very low, and then you look at the stress between the grout and the ground is also very low. So because you've got such a large perimeter, you're not actually worried about the unzipping, if you like, of the pile itself.
Right. And the in situ version, then, how does that actually work? Is there a...
So the in situ version is much more simple. So we put in, we drill the pile, we do a steel liner, a thin wall crinkly tin liner, 1.5 mil thick galvanized steel, and that comes with welded joints, very finely welded joints, and we bolt those joints together. We trap them off and we lower one down, trap them off, lower one down. We put that back down onto the bottom, and then we just put a simple normal Tremie pipe in down the side of the pile. We concrete up to a certain level. We take the Tremie pipe out. We put our reinforcement cage in, which is limited to around about 10 meters depth on the in situ version, and then we concrete up the last 10 meters of the pile itself.
So how do you make the tube inside?
It's galvanized steel concrete.
On the inside and the outside. Just on the inside.
Just on the inside. We don't concrete in the middle. We just concrete around the outside.
Okay.
And use some reviews on
it's a normal piling. It's a normal piling mix. So it's a high slump. Yeah, F flow mix potentially as well. Yeah.
If you mute yourself, I'm just
yeah.
Okay. Thanks very much. Thanks very much, Stuart. That was an excellent presentation, and certainly open to plenty of challenge from the audience.